Welcome to this introduction to complex analysis, where we explore how complex numbers, multi-valued functions, and the Cauchy-Riemann conditions reveal the hidden geometry of the complex plane. Complex numbers extend the real line into a full two-dimensional plane, where every point has a real part and an imaginary part. In this plane, we can add, multiply, and even invert numbers just like ordinary arithmetic, and each number has a natural mirror image called its complex conjugate. A complex function assigns a new point in the plane to every input point, splitting naturally into a real part and an imaginary part. Some functions depend only on the complex variable itself. These are the holomorphic functions, the most important class in complex analysis. We can also describe complex numbers using magnitude and angle, a polar picture that reveals their geometry. This leads to Euler's beautiful insight. Complex exponentials encode rotations in the plane, unifying algebra and geometry in a single formula. The complex logarithm reveals one of the most surprising features of complex analysis. When we write a complex number using its magnitude and its angle, taking the logarithm splits it into a real part and an imaginary part. But the angle is never unique. You can always add a full rotation without changing the number. Because of this, the complex logarithm doesn't have a single value. It has infinitely many. Each choice of angle gives a different branch of the logarithm. This idea extends naturally to the complex square root. Just like a real number has two possible square roots, a complex number also has two possible values. These come from the same ambiguity in the angle. Shifting it by one full rotation flips the sign of the square root. So the square root is a two-valued function, while the logarithm has infinitely many branches. In the real world, expressions like 1 raised to any power are simple, but in complex analysis, even this basic identity breaks down. The reason is that the number 1 can be written in infinitely many exponential forms, each differing by a full rotation in the complex plane. When we raise 1 to a complex power, each of these forms produces a different result, giving us infinitely many possible values. This phenomenon extends to any positive number. Even something as familiar as the number e acquires infinitely many branches when used as a base for complex powers. And when we start composing these powers, like raising ez to the power z again, consistency becomes crucial. Only by choosing matching branches do familiar identities reappear. Complex powers are therefore fundamentally multi-valued, and managing their branches is essential. To define a derivative in the complex plane, we can't simply copy the real definition. A small change in a complex number can point in any direction, not just left or right. For a complex derivative to exist, the result must be the same no matter which direction we approach from. When we express a complex function in terms of its real and imaginary parts, comparing the limit along the real axis with the limit along the imaginary axis leads to a remarkable conclusion. The two parts must satisfy a pair of strict compatibility conditions. These are the Cauchy-Riemann equations. A function that satisfies these conditions is called analytic or holomorphic. Such functions are extraordinarily well-behaved. They're smooth, infinitely differentiable, and tightly constrained by their values in any small region of the complex plane. Let's look at 4 examples to see how the Cauchy-Riemann conditions decide whether a function is analytic. First, the function that squares a complex number behaves perfectly. Its real and imaginary parts fit together exactly the way the conditions require. This makes it analytic everywhere, an entire function. Second, the reciprocal function also satisfies the Cauchy-Riemann conditions everywhere except at the origin. That single point breaks analyticity, giving us a simple pole. Third, if we take the complex conjugate, analyticity fails immediately. The function depends explicitly on both the real and imaginary directions in a way that cannot be reconciled. Finally, the product of a complex number with its conjugate looks smooth, but it too breaks the conditions, except at a single point. These examples show how strict holomorphicity is. Even small deviations from the ideal structure destroy it. One of the beautiful consequences of the Cauchy-Riemann conditions is that the real and imaginary parts of any analytic function automatically satisfy the Laplace equation. In other words, they are harmonic functions. This means that holomorphic functions are deeply connected to physical systems governed by potential theory, such as electrostatics, fluid flow, and heat diffusion. The conditions that guarantee complex differentiability also guarantee that both components of the function have zero curvature in the plane. This reveals why analytic functions are so rigid and why their behavior is so tightly constrained. Their real and imaginary parts are harmonic partners, each determining the other completely.